A quick bit of background on what this video is all about. I decided to make a video just describing the basics of perspective and orthographic ways of depicting three-dimensional space that we occupy here on Earth. And I was inspired to make this little video because of this bit of video clip I'm going to play for you, about a minute's worth here, from one of Ranty's recent shows with Brandon Toy standing in for Ranty, although Ranty is also participating. They took a snippet of a video of mine that I had prepared earlier with my permission and played a bit of it, and then they discussed the diagram that you see on the image of the screen here, which is an orthographic view, a side view of a diagram indicating an observer looking over an obstruction to a target object in the distance. So I'm going to play about a little under a minute of this clip, and then we'll embark on the rest of this video.
Okay, well, let's give that diagram the thought that he asked Ranty to give it. And what do you guys think about this little orthographic diagram here that he shows?
Well, he's put in a perspective. Well, he's put an orthographic view without putting any perspective in.
Yeah, bingo. Yeah, absolutely. This is ridiculous.
You know, he's not reduced the height of the objects as they get further away.
He's applying Euclidean geometry to a site observation. Period. And this is the Globers keep doing this. They just cannot let go of the Euclidean geometry, and this is the trick. So
the cool thing is where is his horizon?
Yeah, his horizon is always below him in this picture. Right now, he does have this. This is just showing the angle down to show what this blue triangle, whatever the heck it's supposed to be, how much that would block, which that's not accurate, right?
Completely wrong. Absolutely wrong. He's completely lost all perspective. There is no account for perspective there.
Yeah, so the bottom line is this is wrong. Any other thoughts on that last 5 minutes of that video?
Okay, that's enough that I'm going to play there. I'm not really interested in addressing in this video what's right or wrong about that diagram, which I would like to say is correct. I will maybe address that in another video. I don't particularly feel any need to address their critique of my diagram, but I wanted to raise the point because Ranty said something about both perspective and orthographic view. He said that I did not include the perspective in the orthographic view. Well, this video that I'm making now is all about that because they are mutually exclusive. They are simply two different ways of communicating three-dimensional space, and they are simply both diagrammatic. Neither is realistic. They're both simply conventions for communicating from one person to another something about the reality of the three-dimensional world that we live in. So we will now embark on a little history, a little overview of what are orthographic drawings and what are perspective drawings. I hope you enjoy. Let's start with the definition from a dictionary. This is from Encyclopedia Britannica, and this is what they have to say about what they call isometric drawings. We have diagrammatic views of a rectangular box with a circular tubular thing coming out of the top. We have a top view, front, side. You can read the definitions if you want. I'm not going to dwell on these slides. They're just here for quick reference. You can pause the video and read them if you'd like. I've put up here a engineer's scale. And my point with this little image is that these objects that we see drawn here in isometric or orthographic projections can be measured with an engineer's scale. I can take a scale and I can put it on a sheet of paper and take that length and translate that to my manufacturing equipment, and it will produce a box of that dimension. I can actually measure with an engineer's scale from this and fabricate an object of exact, precise dimensions. That's what an isometric or an orthographic drawing does, which is not what a perspective drawing does. Here is the Merriam-Webster definition of orthographic projection, for those who wish to see it. And the main point I'm going to drive home here, and it'll come up again, is that we have essentially two different ways of portraying three-dimensional objects. We have orthographic views and we have perspective views. Perspective views give us an impression of what we see. They match what we see as we move through space. However, perspective views do not provide the numerical data, the measurable data that is needed to recreate objects. So you will find, for example, this lovely little book from 1922, which I have in my digital library. It's a training for how to draw houses for architects. It includes this delightful page that's got a nice summary of both orthographic and perspective approaches to drawing. So we see orthographic projections down at the bottom of the page. In the middle, we have isometric and oblique drawings, and at the top we have a perspective. And the thing that you will, and let me move on to the next page here. I've overlaid these two little red lines on this isometric here on the left to indicate the essential difference between isometric and perspective. This drawing represents a box with flat parallel sides. Parallel lines, by definition, do not converge in the three-dimensional world we live in. So this drawing, the isometric, draws lines which in reality are parallel. It draws them on the page in parallel. I've extended those with these little red lines. No matter how big your sheet of paper, if you're drawing an isometric, you draw the lines parallel. They do not ever touch. And they maintain the distance that they actually measure in physical space. Whereas the perspective view gives us the impression that parallel lines do converge out at the horizon. Now that's the way things look to us with our eyesight, the nature of our eyesight as it is, human eyes. I've often wondered, a little aside here, I've often wondered what the world looks like to animals that have very different eyes than us. For example, fish with eyes on either side of their head. How do they perceive space? They must have well over 180-degree field of view. I wonder what it's like for them. Anyhow, this is a way of portraying space as it's seen by the human eye. But if you were to take that engineer scale that we saw in an earlier slide and put it on this drawing, you'd have a hard time getting dimensions for that box. If you needed to fabricate that box, you wouldn't really know how tall it is or how long it is, because it's constantly changing. Whereas if you had an isometric drawing, you could put your ruler against it and you'd know the dimensions. So this page is a nice summary of the key differences between those two types of drawings. And this page, as a follow-up, I think is also nice because it shows it as applied to a simple little house. Lovely little book on the website archive.org. Any of you who are interested in architecture, I encourage you to go there. The same book then takes those drawings, which it introduced, and shows how they are used to make a house. Now, this is the first page, and it includes this lovely page on the left, which I'm going to snip out and rotate so we don't have to look at it sideways. There you see it a little bit larger. It gives us a perspective view in the middle with an elevation on each side. The elevation on the right is showing the faces of the walls that are pointing towards the right. The elevation on the left is showing this little piece of wall that faces left. And at the top of the page, we have the plan view. A plan is nothing but an orthographic drawing where we're viewing it from top down. So in order to draw this perspective accurately, and I don't just mean a very nice artistic freehand drawing, but a precise mathematical perspective, in order to do that, you have to start with orthographic drawings because you need the data, you need the numbers, you need the actual physical dimensions of the object in the world. So you start with an orthographic drawing of the plan. You place your viewpoint, that's marked here in the middle of the page with S. That's where the person is standing and looking at the house. You place your viewpoint at the same scale as the plan drawing, orthographic, onto your plan. And then from the viewpoint, you can trace the lines, which are the line of sight, to each corner of the building, to each edge of the window. Where those lines intersect this imaginary plane, this line that's crossing here, which represents the paper, those intersection points help us to build this perspective. So the message here is that in order to draw a realistic perspective, we have to start with orthographic drawings. We have to use Euclidean space. There's no getting around it. That's how you draw a perspective. Now, if you were to hand this perspective to a builder and say, I'd like you to build this house, he'd be pushed out of shape, I think is a nice way to say it. Without plans, without elevations, without the dimensions on the drawings, accurately scaled floor plans, accurately scaled building sections, you could never really build a house from a perspective drawing. I mean, a really super good builder could probably kind of reverse engineer your perspective and develop plans and sections and elevations, but it'd be a hell of a lot of work and a big headache, and they really would not appreciate it. They don't want perspectives. Reality is an orthographic drawing. If you want measurable reality, you need an orthographic drawing. Here are the tools that those drawings were made with. Simple analog tools. This was 1922, back in the day before anything digital existed, so there's no funny CGI going on with any of this stuff. These are just pens and pencils and rulers and triangles. And then the book goes on to give us nice examples of plans. Another plan, an elevation on the right side here. Note that all these drawings are orthographic and that these are the drawings a builder would actually use to build the house. You will see that perspectives do not appear in there anywhere. This is a lovely drawing. It's a one sheet which contains 2 plan views and 2 elevation views. One elevation on the top right is a cut section through the wall and through the roof. The other half of the drawing, on the bottom right, shows the elevation of that same section of building, that same piece of building, which is a sort of a bay window that sticks out of the house. And on the left side, we've got the roof and a plan cut through the walls. So that's orthographic drawings and how they're used. Every modern building that exists today was built using orthographic drawings. That they would never have been able to build them otherwise. They do not mix orthographic and perspective drawings. When a builder is handed an orthographic projection of a building, he does not get something that mixes perspective into it. So this notion that a diagram is in some way inaccurate because it doesn't mix perspective with orthographic drawings flies straight in the face of the reality of every single modern building in this world today. So I don't know where Ranty and Brandon live, but in this world, we use orthographic drawings because they're measurable. Here's a perspective drawing from the 1480s, a perspective painting from the 1480s by an artist named Perugino. Perugino was a disciple of Filippo Brunelleschi, who is sometimes credited with inventing the rational geometric approach to perspective drawing that we use today. It did not really exist in its most rationalized and accurate form before Brunelleschi. There were artists in Italy during his lifetime and just before who were starting to reach for it and begin to develop an understanding of it, but not an accurate understanding. It was Brunelleschi who was probably responsible for really developing the systematic geometric understanding of how perspective works in a Euclidean space. So Brunelleschi did not leave us any drawings. He was primarily an architect, and he left us several beautiful buildings, but his work as in perspective was carried on by his students like Perugino. So this is a painting by Perugino from 1480. Here we have a painting from the 1450s. So after Brunelleschi had already started working with perspective, and this artist, if I can remember the name, Giovanni di Paolo, 1454. This artist was clearly trying to get it, but was not there yet. His vanishing points go off in all different directions, and he's clearly not got the rational approach that Brunelleschi developed. This is an ancient Roman example, 1st century BC from Pompeii. And again, it's an interesting thing because you don't find the really correct perspective that we use today before Brunelleschi or anywhere else in the world. It did not exist in other cultures. There were attempts and approximations, such as this Roman one, where we see that the converging lines at the bottom of the image don't match the converging lines at the top. They had begun to grasp the idea, but they never thoroughly rationalized it. This is a Chinese example from the 11th century, 12th century Chinese example. And again, we see it's actually more along the lines of an orthographic view than it is a perspective view, because we see that these angled lines, which represent parallel objects in reality, are also parallel on the page. So they had kind of not quite grasped the difference between orthographic and perspective views when they created this art. This was China in the 12th century, and this is China in the 11th century. Again, we see that they're using an orthographic projection rather than a perspective. Now, orthographic drawings, perspective, so basically perspective didn't really exist as we know it. It wasn't used as we understand it today before the early 1400s in Italy. Orthographic drawings have a long history. So this is a page from the notebooks of Vial de Honcourt, who was a mason, master mason of the 1200s, 1200 to 1250 he lived. And he's one of the few who left a book of his sketches. It's a rare survival. And it contains plan views. We see plan views of columns over here. These are several designs for columns showing them cut in plan. So horizontal orthographic view. These are additional window mullion designs. And then on the left side of the page, we get elevation view. So what we have are plans and elevations drawn without perspective. They are orthographic views, and these are the kinds of views that people like the master masons of the Middle Ages used to organize their ideas when they were building the great cathedrals of that period. We can go much further back than that. This here is the plan of St. Gall, which is a monastery in Switzerland, in the town of St. Gallen. And this plan drawing is diagrammatic in one sense, in that they did not bother or attempt to draw things like the thickness of walls. However, it is actually to scale. It's a to-scale drawing in that the floor dimensions are accurate and the relative sizes of every building on the plan are proportional to each other. A good builder could take this plan, especially at that time, a good builder could take this plan and construct this whole monastery. The plan of St. Gall dates from the 800s, and it was intended primarily as an organizational document, a kind of a site plan and a model. The actual monastery that was built at St. Gall contains elements from this plan, but it was not actually this precise plan that was eventually built there. But that takes us back to the 800s, and that's a plan view, which is an orthographic view. But we can go much further back than that. We are now looking at 1150 BC. This is an ancient Egyptian papyrus that is an extremely rare survival, in which this papyrus also contains to-scale dimensionable drawings. They were made to scale, including wall thicknesses, of a tomb. This part of the drawing shows a tomb. Of the papyrus has many parts, and this is one part of it. So what we have are the several different rooms of a tomb that are stepping back, and they're cut into rock. And this red ochre indicates the rock that they've been cut into. There are walls separating each space. The doors are drawn diagrammatically on the flat, sort of laid down on the floor to give a sense of where the doors are located and their general size according to the walls. And it's all scalable. You could actually build a tomb that matches that. This is from the same papyrus. And what we see here is a plan view, again, I would call this a map now. So we've moved from the scale of a building to the scale of a small landscape. I believe this covers an area of some 15 acres, which is several hectares. I don't remember the conversion right now. I think that's about 4.5 hectares. Anyway, it's a sizable piece of land, and it's a map of that piece of land, and it's accurate and to scale, to the point. It's enough detail and well enough, properly enough scaled that the archaeologists who discovered this papyrus were able to identify the location that was drawn. And it indicates waterways and roadways and fields and buildings. And it's accurate. It's a map. With this map, you could take point A to point B. You could measure it off the map. And then you can go out there and measure the distance on the ground. And the distance would match according to the scale. So that's a plan view, an orthographic view. And the only reason why it works is because you can scale it. And the only reason why you can scale it is because it's not drawn in perspective. I want to end with one last thought, though, and that takes this discussion to the next level. And that is that the world we live in is not a Euclidean space with 3 coordinates x, y, z, which are at right angles to each other. It's a sphere. Now, you may or may not like that. Doesn't matter. You may not even agree with me. That doesn't matter for the purposes of this discussion. The reason why I'm raising it is because all of the perspective issues I've been talking about actually do assume that it's an XYZ 3 right angle Euclidean geometry space and do not recognize the fact that it's a sphere. So all those perspective drawings we were looking at are in fact not 100% accurate. But the key is that they are drawings of things like individual buildings or a small landscape of a few miles where we see just a few buildings. And over those short distances, the inaccuracies connected to the difference between a flat plane and the curved surface of the Earth are too small even really to draw correctly. You would not be able to accurately draw the 8 inches drop of the ground a mile away if you're drawing a picture that shows something in the foreground and something a mile away. You just couldn't draw it that carefully in the first place. So you don't need to have the complications of real spherical geometry when you're doing those perspective views. Nonetheless, those real spherical geometry views are what we see if we understand what we're looking at the Earth. And Jos Lies did a pair of these beautiful videos, and I'm going to play a little bit from just this one. Actually, maybe I'll just go ahead and play the whole thing. Thank you, Jos, for the use of this video. I didn't ask your permission in advance, but I will let you know, and I hope you don't mind. It's one of my favorite videos. So we're going to see what it actually looks like. And yes, you do see the curve. And it's quite a wonderful thing to see.